basically, when you think of uh, technologies that help humanity and like save the world, what comes to mind? I think some numbers on philanthropic giving to science are revealing. 90% of the philanthropic dollars that go towards research goes towards health technologies. Of that 10% that's remaining, a vast majority of it goes towards climate technologies. That's another way. But none of this is possible without advancements in materials and manufacturing technologies. So to be very provocative, I want to argue that the technologies that go into making the materials and getting the materials and then making the chairs that you're sitting on are more important for human progress than the smallpox vaccine. So take stainless steel, for example. You think of it as a thing that you make pots out of, makes nice sinks. That's great. It's also critical for making the syringes that you use to deliver a vaccine. Without that, you would have, you'd be sticking rusty needles in people's arms. It's also important to make the stainless steel vats that we use to produce the vaccines. Stainless steel only invented in 1915, and already critical for all of these technologies that we think are part of the future. Going farther back, we think of the power loom, right? People used to have one pair of one set of clothing. The reason we have collars is because you need detachable pieces of clothing that you would, like the dirty parts, so you could take them off and wash them more frequently, because you don't want to wash your clothes too much because you only have one and you'll wear it out, and you can't afford a new one. New manufacturing technologies allowed us to clothe people and keep people from freezing to death on the street. Going farther back, iron. It allows us to cultivate many, many, many more kinds of soils than we could previously and make things like, nails. Going even farther back, you have bronze, which is really the first thing that allowed us to cultivate crops en masse, drastically increasing how much food we can produce and, allowing people to not starve. Going even further back, you have stone, and the ability to manufacture stone into tools lets humanity conquer the world, right? So we literally name ages after materials because of how fundamentally they are to progress. And the thing that I want to flag is that this progress, it's not inevitable. We think of it as if it is, but I want to just give you, both try to convince you of the importance of materials and manufacturing, give you a small amount of sort of like a sense of what that actually entails, because most of us are so separated from these technologies that we don't have a good intuition for them. I want to sort of outline why there's a particularly large amount of friction on these technologies in the 21st century, and then sketch out what we at Speculative Technologies and other places are doing to try to address those frictions. When I say materials, what do we mean? It's just materials is like the stuff that we make things out of, and manufacturing is how we turn that stuff into those things. And often we think of them as just like separate things. I want to argue that they really are deeply interconnected, like an Ouroboros, because often in order to harness a new material, you need to develop a new manufacturing process, and similarly, a new material can enable a new kind of manufacturing process. One example is steel. So before what is called the Bessemer process, which is how we make a lot of high purity steel, we can make steel, but it was extremely expensive. So you'd only use it for either things that are like flaunt your wealth, or things that would save your life, like a sword or a piece of armor. I forget the number that Casey mentioned earlier. Once you create the Bessemer process, it allows steel to become this thing that we, like, per capita, we use, like thousands of tons per person. And so that's just to illustrate like how they're really coupled, right? Like, is the Bessemer process a materials innovation? Is it a manufacturing innovation? They're really sort of the same thing. Another example, something that we're working on is protein-based fibers, right? So protein-based fibers are like spider silk is sort of your classic example of a protein-based fiber. You think of this, and if we could get them to work, you could potentially make things that outperform Kevlar, allow you to have things that have the properties of polyester without microplastics, make biologically active fibers, lots of great stuff, right? That's a material, but the challenge in actually making this happen is a manufacturing process. Spiders do this cool thing in their abdomen where they actually like line up all the proteins just so, and then apply like a time-varying stimulus that causes them to bind together into that fiber, right? So again, so we're trying to make a material, but it's actually a manufacturing challenge. And so together, materials and manufacturing, they kind of circumscribe what we're capable of as a civilization. That plus the secret third ingredient is energy, very important as well. So like I'm talking about this in abstract, I want to just tell a couple of stories just to give you a sense of like what it looks like for a new material to come into the world. So let's talk about carbon fiber. 1958, in the lab, people are able to make carbon fibers with like 20% carbon, right? So that's like proof that you can make fibers out of carbon at all. 2 years later, then they need to spend a lot of money and do a lot of work just to make fibers that are actually fully carbon, right? Like this is what you need to make it work. 8 years later, it took them 8 years from when they actually had a fiber that like roughly had the properties that you wanted to make carbon fiber fan blades. This was Rolls-Royce. It almost bankrupted them because it did not work. And so you could easily imagine a counterfactual situation where people are just like, carbon fiber is garbage. Those carbon fiber fan blades didn't work, and just abandon the technology. Luckily, in parallel, the Japanese were working on carbon fiber yarns, which were then used for like very low margin insulation, not very impressive stuff. Remember, this whole time, the people working on this had an idea that if we could master carbon fiber, we could use it as a very strong lightweight material. 5 years after that, you have the first example of carbon fiber being used in something actually useful. So it was used in a golf club. Not until 2009 do we get the first carbon fiber commercial airliner. People had made airplanes out of it before. But I just want to like, it takes a really long time and a lot of work and a lot of failure for these things that like feel like it was inevitable. It's like, oh, of course we're gonna like put carbon fiber in airplanes. Another example, and just to like give you a sense, like this is the process of like just making carbon fiber composites. Not even like you have to do a whole bunch of stuff up here before you even have the carbon fiber. Let's talk about stainless steel. 1798, they isolated chromium as like an element. They're like, oh, there's this thing called chromium. That's neat. 1815, they realized that, oh, if we mix this chromium in with iron, it doesn't rust as much as iron. 1850, so 35 years later, they were like, oh, maybe we can use this in steel. And so they were just kind of like randomly mixing chromium into steel, and it didn't work very well. Again, this is one of those situations where, like, you know, if you wanted to go off of track record, you could say like, oh yeah, like this chrome steel thing, like, meh. Took another 48 years before Carnot, so like cycle Carnot, discovered that the problem with that earlier chrome steel was that it had too much carbon, which caused it to lose its corrosion-resistant properties. And then simultaneously, you needed this manufacturing process to actually make chromium with less carbon. Like all the chromium previously had been contaminated with carbon. Again, look at like I just want to like the tight coupling between manufacturing process and materials, right? Like we don't get stainless steel, the material, without a manufacturing process to make a different material with the right level of purity, right? Like you cannot decouple these things. And finally, in 1915, they patented it and started using it for everything from cutlery to syringes, and it's awesome. And then on the manufacturing front, I just wanted to like give this is if you explode out a refrigerator, this is just like all the parts. And I just want to like walk through just some of the manufacturing processes that are used in these, right? So like the outside's probably plastic injection molded. The little casing for the motor is cast. That's probably a part that's been like powder coated. That part's probably stamped out on a machine. The stamp for the machine was probably made on a CNC mill. That part's being like bent. And then if we just look at like the list of all, I went to a trade show recently, and if you look at, that one's extruded, the wires are extruded and round. And if you go to a trade show, like this is just a list of all the different like processes that people have entire businesses devoted to. So just like underlying all this stuff around you are so many different ways of like turning stuff into things. And so, this is all good today. I want to like, I'm sure you've all seen this image. I want to take it seriously and be like, okay, what do we need to do to actually make this world real? Right? So like that building is probably made out of transparent diamond manufactured by nanobots. The little robotic dog like needs much higher torque actuators, so it probably needs magnets that are even better than what we make out of neodymium. Like that maglev probably needs room temperature superconductors. That nice fancy floating car there is probably created on demand by a black box factory for the person walking the dog. And, those flying cars, they might be powered by antimatter, and you need to both figure out how to like manufacture antimatter at scale. Currently, we can make like 10 to the -7 kilograms of it, maybe less, maybe it's 10 to the -9. And we need to figure out new materials to contain it. So obviously I'm being facetious. Like this is not like predictive, but I think we forget how important materials and manufacturing will be to building the future. And so I hope that I've vaguely convinced you that materials and manufacturing are kind of like engines of progress. But the reality today is that engine has kind of stalled out. Like an engine seizing up, it is like friction upon friction upon friction that has caused it to stall out. And I could list sort of a whole bunch of these things, be very abstract. That's generally how I think. Instead, I'll tell you just a couple of stories about that sort of illustrate these frictions. So this first one is actually like heavily redacted, so that I don't violate any NDAs. But imagine that you're trying to make this MacGuffin, right? And this MacGuffin is a thing that many people have dreamed of. We think of it as part of the future. A company actually managed to make a prototype of this MacGuffin that really worked. It was incredible, but making this MacGuffin involved attaching like this one widget to another widget in a very specific way that was done by this one technician who had the magic hands. And not only could this company not figure out how to manufacture, like bind these two widgets together to manufacture this thing at scale, but the guy who could bind them together couldn't even like teach someone else how to do it. And ultimately, they raised so much money that they were under so much pressure from investors that they just like abandoned that technology altogether and used off-the-shelf parts to make the thing. And it did not realize the dream of the MacGuffin. But the lesson there is that like making something manufacturable takes a lot of time and a lot of uncertainty and a lot of money. And more like and often more so than a startup which sort of needs to grow can really do. Another example, I used to help people start companies in Singapore. And people would come to me and they'd be like, oh, here's my idea. And I would talk to them and I'd be like, okay, I have two hats. I have my investor hat and I have my Ben hat. First, I'm going to put on my investor hat. And I would say like, this is not a good idea. Like you should not start a company around it. It will be too low margin. It will take too long to get out into the world. Like the companies that you want to interface with are too risk averse to start doing this. There are like all these hidden requirements that you need to hit. Just like, I don't know, don't do this. This is not a good idea for a startup. Like no one would invest in this. And I'm like, okay, cool. I'm gonna take off my investor hat. And I'm gonna put on my Ben hat. I'm like, this is freaking awesome. Like this needs to happen. I don't know how you're gonna make this happen, but you need to do this. And this happened over and over and over again. And so the fact of the matter is the like I don't know how many of you have seen the Valley of Death, but basically it's this idea that like there's stuff that's like really researchy, and we have there's government grants and people like the sort of things that you can do in academic labs, and then there's stuff that is a good investment. And between the two, you need to do a lot of work and put in a lot of money, but it like doesn't give people the warm fuzzies of funding research. It also is not something that like a rational investor would put money into. And this Valley of Death is particularly large for materials and manufacturing technologies, and it has gotten wider over the 21st century through a combination of various frictions on getting things out into the world, the way that we finance new technology, and a number of institutional factors, what is incentivized in academia, all of that. And so want to do something about that. So my approach to this is always sort of like, look at the past. And so asking the question, like, what do environments that unlock materials and manufacturing technologies look like? I'm very much not in a, like, who was saying yesterday that progress is kind of like a solid state rocket. I think it was Patrick Collison quoting John Collison. And I very much agree with that, right? So the point of this question is not like, what should we replicate? It's like, what are the like underlying pieces that we can try to riff off of to make these environments? And so sort of like two sort of like really like classic good examples of environments that unlock this well. So like when one is when they're scaling up the Haber-Bosch process. So Haber-Bosch is the process that we use to fix nitrogen. It's how we get all our fertilizer and how we're alive. So Franz Haber had discovered, oh, okay, you can discover the process, but one, it used osmium as a catalyst. And what they realized at BASF was that even if, like, they literally bought all the osmium in the world, like literally all the osmium in the world, and they're like, wait a minute, even with all the world's osmium, we cannot scale this process up enough to for it to be useful. And so they so they needed to do like this like deep research to figure out like how do we make a catalyst that doesn't require buying all the osmium in the world. And eventually they figured out an iron-based catalyst, but it was like it was real research. And similarly, as they scaled the thing up, they like the tanks started exploding. Because the hydrogen that they're flowing through it would weaken the metal. That's just a thing that hydrogen does to metal. And so they needed to like come up with like completely new processes to jacket the metal and shield it so that the tanks don't explode. And the point here, like they were doing many things simultaneously, right? Like they were actively trying to make the process do something useful. At the same time, they needed to be doing like deep, like technical scientific research and all these experiments, and throwing capital at the thing. And another example, like, okay, we all know Bell Labs, yada yada. The particular example that I love from Bell Labs is that when they were working on the transistor, they needed to, like they're having this they need to have this junction between the semiconductor and a metal, and at the time it was like they didn't know how to do that, and so they went to the machinists and they're like, what do we do? And the machinists were like, oh, okay, like I can actually poke at this, right? So you have the PhD gigabrain scientists going into the machine shop right down the hall and getting help to be able to do that. And so so there's a couple of takeaways from these environments. One of them is having research, prototyping, and manufacturing in the same room. To a large extent, we have outside of startups, we've really decoupled these things. Right, so we expect people, there's the whole idea of like, okay, you'll create the material in your academic lab, and then you'll like spit it out and start a thing. You don't have these loops where where you're simultaneously working on doing the thing at scale and doing research at the same time. Another one is just like they very consistently like empowered individuals to get stuff out the door quickly. Like when they're going to the machinists, it wasn't they were like, oh, like let me put in a change order that like goes to the machine. They just walked down the hall and like got stuff done. And then the third one is while you're moving really fast, all these organizations were thinking about very long time scales. And that's a real tension. And like that's really what we're trying to build at Speculative Technologies. We're really trying to build an environment like that. So I describe us as a nonprofit industrial research lab. I'm not sure if that's the best way of describing it, but it is hard to put words on things that are new. So like, for example, to go back to that protein-based fibers program that I mentioned earlier, just to like give you a sense of like the sort of stuff that actually needs to be done is we both need to like actually create like new computational models of structural proteins, right? Like AlphaFold is great, but generally it's modeling proteins that are in solution. But there's a lot of proteins that we use in nature that actually turn into materials. And so that is like this like deep research project that we need to do. At the same time, we need to figure out how to integrate those proteins into a manufacturing process that can operate at scale, right? Like nobody will buy a spider silk jacket if it costs $50,000. And so, and there's just like many examples of places where this kind of work needs to happen, and we are pushing towards that. But we're not the only place. There's not just one intervention that needs to be done. As I mentioned, like what has happened is that we have built up all these different frictions in all these different places that need to be addressed, right? So we need work like the folks at Institute for Progress, like reducing how much it costs to make a factory, right? Like that actually is a big reason why it's hard to get things out into the world is like you need, if it's extremely expensive to make a factory, it's extremely expensive to try to figure out how to scale something up. And so you need to be very certain that scaling it up will actually yield the results. And so like that sort of back propagates through the sorts of things that we get out into the world. And just like, yeah, we need a flowering of new institutions to address these things. And to sort of start wrapping up, I think a lot of people still have this sense that like materials and manufacturing processes, like they're sort of inevitable. And it's hard to think about counterfactuals. But I think an interesting counterfactual is the Anchithera mechanism. If you're not familiar with this, it is this like sort of like it's vaguely we're not quite sure what it was used for, but it was like this very intricate mechanism that was discovered in a Greek shipwreck in the Black Sea. And the fact of the matter is that so it'd been done, it has these like very complex gears that we think look very modern. But they were all manufactured by hand, right? Like this was like someone like actually carving out all these gears by hand. And you could imagine like this a very different world where if like the Greeks figured out a scalable manufacturing process for things with this precision, we would have had like stopwatches in ancient Greece, and it sounds like, right, like that sounds absurd, right? But I think that is to some extent the nature of counterfactuals in these like deeply important things. And so I sort of just think about like, okay, what are the counterfactuals? Like, what could we have if we reduce the friction on materials and manufacturing? And really to close, Patrick Collison was talking about how progress studies ultimately is about vibes. And so, in addition to try to convince you that this stuff is cool, I just wanted to close on like the vibes of like materials and manufacturing are the thing that will let us open up new frontiers, and those new frontiers are then what will unlock human progress. And so, if nothing else, I want you to like look around the world with like new awe at what we can do with stuff and turning it into things, and just like go out and do awesome stuff. Thanks.